Welcome! In this brief video, we will introduce the concept of the percentile, how to calculate a percentile for a given data set, in other words, locate the data point inside the data set, and how to determine which percentage is associated with a given value in a data set. As we saw in the last video, the median is actually the 50th percentile, so percentiles give us another way to think about the median. However, they have far more uses than the calculation of just this one measure of center. Again, the median is the 50th percentile. This is the value in the data set for which at least 50% of the data fall at or below this value. While 50% is associated with the median, we can talk about percentiles for any desired percentage value, such as 10%, 25%, or 99%. Our working definition for a percentile will be as follows. The kth percentile, denoted capital P sub k, is the value in the data set for which at least k% of the data is at or below that data value. To clarify, we use phrases like at least and at or below, equivalently at most, to quote-unquote hedge our bets, just in case there are repeated values in the data set. For example, it may be the case that 43% of the values are strictly less than your given value, but 51% of the values in the data set are less than or equal to your value. We'll see more examples of this shortly, but for now, we will just note that this is something to keep in the back of our minds. Before we proceed, we need to introduce a variation on the index notation we've been using. Let's start with a very basic and very small data set. Here we have the results of rolling a 6-sided die 5 times. As is often the case, most data sets, as they are constructed or recorded, are not ordered. Here we have a 5, a 1, another 5, a 3, and lastly a 2. Using our index notation, we could write the data set as shown here. X sub 1 equals 5, x sub 2 equals 1, all the way up through x sub 5 equals 2. Now, if we put the data in order, 1, 2, 3, 5, and 5, then we use a slightly different indexing notation. To indicate the location of a data value in a sorted data set in ascending order, we wrap the index in parentheses. Here the ordered x sub 1 is 1. The ordered x sub 2 is 2. And so on. Note that the indices have been wrapped inside of parentheses, x sub parenthesis 1, close parenthesis. While x sub 4 was 3 in the original data, x sub parenthesis 4, i.e. ordered x sub 4, is 5. To clarify, ordered x sub 1 equals unordered x sub 2, which is the value 1. And ordered x sub 4 and x sub 5 are the same as unordered x sub 1 and x sub 3, which are both the value 5. Thus, the last two ordered values are actually the first and third values in the original data set with the original unsorted order. Now that we have that notation available to us, let's work through an overly simplified example to demonstrate this using a very small data set. For a toy data set, we will use the first 10 products of consecutive Fibonacci numbers. This small data set of 10 values is 0, 1, 2, 6, 15, 40, 104, 273, 714, 1870. Fortunately for us, the data is already in ascending order. X sub paren 1 equals x sub 1, x sub paren 2 equals x sub 2, and so on up to x sub paren 10 equals x sub 10. If this were not the case, the first thing we always do when working with or calculating percentiles is to sort the data from the smallest to the largest. The method I will introduce to calculate the percentile given a value in the data set will be as follows. Locate the first occurrence of that value in the data set, then, counting the value and all the values less than it, divide this count by the total sample size and convert to a percentage. This will tell you which percentile your value is in for the data. So, we want to find which percentile is the value 6 in this data set. We note there are 4 values at or below 6. 4 divided by the sample size of 10 is 0.4 or 40%. Thus, 6 is the 40th percentile for this data set. 2 notes. First, strange things can happen if you pick the minimum or maximum of the data set. For example, 0 has 1 value at or below, so it is the 10th percentile for this data set. 1870, the maximum, has all the values at or below it, so it is the 100th percentile. This feels awkward or incorrect to some people. Thus, there are other definitions of percentiles that can be used. These often involve dividing by n plus 1 or n minus 1 when getting the percent. For our purposes here, we will not dwell on these possible issues, and we will just divide by the sample size. Second, it is also possible to talk about the percentiles for values that are not actually represented in the dataset. Technically, for the definition we've provided, any value from 6 up to 15, including 6 but not including 15, could be considered the 40th percentile for this dataset, as 40% of the values would be at or below such values. Again, we will not dwell on this potential issue of ambiguity in the definition, as it really won't apply to our practical analyses of authentic datasets. That said, for students interested in more advanced statistical and mathematical topics, these are interesting issues to consider and to keep in mind for future studies in more advanced classes. Let's do another example with a small dataset. Here is the first 20 rolls of a 6-sided die. Of course, data such as this is very rarely ever in order, so the first step is to reorder the data. With the data now sorted in order, we will note that there are 5 values that are strictly less than 3. 5 divided by 20 is 25%. And there are 10 values that are less than or equal to 3. 10 divided by 20 is 50%. But if we start at the first time we see the value 3, this is at the 6th spot in the ordered dataset, then there are at least 6 values in the dataset that are less than or equal to 3. 6 divided by 20 is 30%, and by our protocol, we will call 3 the 30th percentile for this dataset. It probably is not surprising that the value we use, 30%, falls somewhere between the strict 25% below and the inclusive 50% below. We will also note that a common variation of this protocol is to not use the location of the first time the value appears in the ordered dataset, but to use the location of the last time it appears in the dataset. This is a perfectly reasonable approach, but we will not be exploring it any further here. Again, recall, 1,000 ways of doing the same thing. Let's walk through the protocol to find in which percentile a data value is located using a more authentic dataset. We will work with the following simulated dataset for the weights of 4-week-old mice. The researcher obtained the mass for 125 mice. We will start with the demonstration where we convert a given data value in the dataset to the percentile in which that value is located. That is to say, we will be given the data value and we will find the corresponding percent for its percentile. In which percentile is the data value 11.4? Another way of stating or asking this question is to ask what percent of the data are less than 11.4 grams. The first thing we will do using our ordered dataset is to highlight all the values of 11.4. Furthermore, we note that the first 11.4 shows up at position number 35. We can tell this because there are 10 values in each row. Using our new notation, we can write the following. X sub parenthesis 35 equals 11.4, which means the 35th value in the ordered dataset is 11.4. Because the 35th value was the first time we encountered the value 11.4, we can write that x sub paren 34 is strictly less than 11.4. And because the dataset is ordered, this would be true for x sub paren 33, x sub paren 32, x sub paren 31, all the way down to the start of the dataset at x sub paren 1. Mathematically, we can write this as x sub paren I is strictly less than 11.4 for all values of I from 1 to 34. So, there are 35 values at and below the first appearance of 11.4 in the dataset. We will take this first position value, 35, and divide by the sample size, 125, to get 0.28 or 28%. Thus, we can say that 11.4 is the 28th percentile for this dataset. This means that there is at least 28% of the data at or below 11.4 in the dataset. Because the value 11.4 is repeated in the dataset, it actually turns out that there are 38 values at or below 11.4 in the dataset, and 38 divided by 125 is 30.4%, which is indeed more than 28%, but that is okay for the manner in which we've defined the percentile. 30.4 is at least 28%, which is to say 30.4% is greater than or equal to 28%. Also, we note that there are 34 values strictly less than 11.4, and 34 divided by 125 is 27.2%. This means there is 27.2% of the data strictly below the value 11.4. We can present this graphically using the histogram for this data set. Here's the relative histogram for this data with a jittered rug plot along the horizontal axis. We have shaded all the bars, or partial bars, associated with the data that is less than or equal to 11.4. The idea of the percentile is that this should represent 28% of the total area under the bars of the histogram. Well, if there are not repeats in the data, this would be 28%. Instead, the area shaded here is at least 28%. And for this particular data set, this actually would represent a bit more than 28% because the value 11.4 did indeed appear more than once in this data set. Before we summarize the protocol, we will clarify the notation we are using. X sub I is the data value of interest, any value from the data set, not necessarily sorted. F is the index of the first spot where this value appears in the data set. Using our sorted data index notation, we could write X sub paren F equals X sub I. K is the percent of the data from F and below. We write the percentile as P sub K. So let's summarize the protocol. Given the value X sub I, any value from the ordered data set, where I can be 1, 2, 3, up to n, we want to find the value F, the position in the sorted data set where X sub I first appears. So we have F for the first spot where it appears in the ordered data set. This means we can write X sub I equals X sub paren F. I will reiterate here that it is essential to have the data set in order when you are working with percentiles. Now there is an immediate implication for this being the first appearance of the value X sub I. In particular, X sub paren F minus 1 would be strictly less than X sub I. In truth, this is true using any sorted data index F minus 1 or below. So the percent associated with the percentile this value represents would be K, which equals F divided by N times 100%. We say that X sub I is the kth percentile for this data set. P sub K equals X sub I. We will note that it is possible to use an arbitrary value as a percentile, meaning a value that is not necessarily in the data set. But in truth, it is not common in practical settings to work percentile problems in this direction. That is, to start with a value in the data set or related to it, if not actually in the data, and then figure out the percent associated with its percentile. At least, if you are looking for such information, you generally don't need the full machinery of the percentiles and percentile notation to answer such a question. What is more common is to be asked what a percentile in the data set is given some desired percentage of the data. And this is where we will pick up in the second part of this video.